Hi, second grade, it's Mrs. Dundore, and I'm here today for a little bit of a science lesson. I know you've been working on sound and vibration with your teachers in second grade, so I thought I'd bring you a little music lesson to go along with that. And you know, I might have told you before that one of the reasons I like music so much is because it incorporates other subject areas. Like music is reading, because in music we read words to songs, which are called lyrics, and we actually learn how to read a whole other language, reading rhythms and notes on the music staff to play songs. So music is also history, because we learn about music from a long time ago and about people who wrote that music called composers. Music is math, because we learn how to count how many beats there are in songs and phrases, and we also have to know how many sounds can go on a beat. It's kind of like working with fractions in math. But did you know that music is also science? Well, it is, because all sound happens through vibration. Watch this. This instrument is called a Vibra Slap. It actually has part of the word vibration right in it. And look what happens when I hit this. It vibrates. Watch. I don't know if you can see it on your screen. And look out, this might be a little bit loud. But see if you can watch it vibrate when I hit this. You can see it a little bit. But what would happen if I put my hand on it while it was vibrating and stopped the vibrations? Do you think maybe the sound would stop too? Let's see what happens. I'm going to stop the vibration this time. So whenever I stop the vibration, the sound also stops, because the sound is coming from those vibrations. I'm going to show you something else to prove that everything that makes sound vibrates. So over here, I have my conga drum. So we're going to have to go down. Yep, that's good. I'm going to put this marker on our conga drum. And if everything that makes sound vibrates, that should mean whenever I strike the top of the conga drum, that should send vibrations through the drum head, and something might happen to our marker. Let's see. I sent vibrations. When it made a sound, the vibrations are going through and shaking the drum head, and you can tell because the marker moves. Watch. Pretty cool. Everything that makes sound vibrates. Okay. You know, even our voices make vibrations. Put your hand on your throat, and then we're going to make a sound. Even right now when I'm talking and going, oh, I can feel with my hand that there's vocal cords inside. When I talk, the vocal cords are vibrating to make sound, and I can feel the vibrations when I do this. Try it. You can feel it because everything that makes sound vibrates. Okay, so did you know that in the air, you can't see it, but trust me, this is the truth. In the air, there are these little tiny things. There's trillions and zillions of them. And they're called molecules. And they're so small that we can't see them. And when something vibrates, like the Vibra Slap, like the drum, like our voice, like our vocal cords, it actually pushes those tiny little molecules. And when it pushes one molecule, that molecule pushes the next molecule. And it pushes the next one. It's like a chain reaction. So that's what happens whenever a sound wave happens. It's bumping into all these molecules. So molecules in the air are invisible, but when that happens and they bump into each other, we call that a sound wave. That's what a sound wave is. And we can kind of see this by using something musicians have. That's called a tuning fork. If I hit this tuning fork to make it vibrate and make a sound, we can't hear anything. Nothing's happening. But it is. We just need a different medium to hear the sound waves through. So we're going to use our whiteboard as one of our mediums for our sound waves to travel through. If I hit the tuning fork on this medium, it should give a way to amplify or make that sound louder. Let's try it. Now that the sound waves are spreading through a medium, our whiteboard, we were able to hear the sound. Let's try a different medium. I'm going to use, well, if you were here, I would let us use our bone as a medium. I'll show you, but you won't be able to hear it the way you would if you were in class. But if I take my arm, which has bones traveling all the way through it, and I stick it in my ear, I wish you had a tuning fork to try this with. It's pretty cool. And I take the tuning fork, vibrate, put it on my bone. I can actually hear the sound from the tuning fork traveling up those sound waves all the way into my eardrum. I have an idea. Instead of bone or the whiteboard, let's try some water as our medium for our sound waves. So as you can see, we have some different sizes of tuning forks here. There we go. So I'm going to set the vibrations in motion, hit my tuning fork, and we'll dip it into our new medium, water. What do you think might happen? Think about what we learned about molecules bumping into each other and sound waves. Maybe we'll be able to see it. Wow, that was very tiny. Maybe we'll try and get a little closer. And I'll give it a nice big strike. There we go. If you can see on your screen, I could see little ripples in the water, and it kind of shot out for just a second because those molecules started bumping into each other. Now I'm going to switch from that small tuning fork to one that's a little bit bigger. Let's see what happens. Maybe more molecules will bump into each other and we'll see more water. Oh, I didn't give it a good strike. A little bit bigger, but I bet this big daddy will go even further, a further, bigger spray. Nope. Oh, wow! That went way out. You can even see drops of water on the piano seat here. Pretty cool. So the bigger the tuning fork, the more it affected and pushed those molecules around in the air. All right. So we hear a lot of sound every day from people talking. So here's a person, his mouth's open. He's going to be talking. Sorry, Mr. Chaddock, for drawing a stick person. And he is inside a room. So here's our room. And when he talks, you know we don't see it, but there's sound waves coming out. And it's moving the molecules in the air. When that sound wave hits the ceiling or the wall or it bumps into some other surface, it actually bounces off. And it starts traveling in another direction. Now imagine this guy is in the PE room or a multi-purpose room or a gymnasium somewhere or a big concert hall. It's going to have all this space to travel through and bounce off back and forth and back and forth, and it bounces in all directions. And that's why when you're in a big gym or something, or like a big cave, and those sound waves are bouncing around, it sounds really muffled and echoey in those types of spaces, because this is what's actually happening. Now let's take our guy out of the gym. Whoops, took his legs away. That's okay, don't worry. I'll give you your legs back. He's not in the gym anymore. He has legs though. He is now going to be in the Grand Canyon. The Grand Canyon, a bunch of rocks and big open space. There's no ceiling, no walls. And there's a sun not in the corner though. And just big open space. So, when our guy talks at the Grand Canyon and the sound waves start traveling, they just keep traveling and traveling and traveling because there's nothing for them to bounce off of until they've reached some surface way far away and start to come back. And all the time it takes for it to come back and then you finally hear your voice again. And that's where an echo comes from. If you're in the Grand Canyon and you yell, echo, the sound waves travel, and then you hear echo, 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 quietly, because they have nothing to bounce off of in a big open space like that. Okay, you know, it kind of reminds me of Google, who's going to help us out with something. I would like to ask my Google. I said I would like to ask my Google, how many miles per hour is the speed of sound?
According to Wikipedia, the speed of sound is the distance traveled per unit time by a sound wave as it propagates through an elastic medium.
Propagate. Okay, that didn't help us, Google.
700.
Listen again.
It's around 700.
How many miles per hour is the speed of sound? There we go.
Speed of sound in dry air at 20 degrees Celsius is approximately 767.269 miles per hour.
767 miles per hour. That's really fast. Some things can go that fast, like some airplanes, some supersonic jets, some bullets can travel that fast. But if you think about when you're in a car, let's compare 767 miles per hour to how fast your parents are probably driving on the bypass in Jacksonville, 55 miles per hour. That's how fast a car is driving down the highway. Compared to 667 miles per hour is pretty fast. Now let's see what the speed of light is. How many miles per hour does light travel?
According to space.com, the speed of light in a vacuum is 186,282 miles per second, and in theory nothing can travel faster than light.
Wow.
Miles per hour, light speed is, well, a lot, about 670,616,629 mph.
Wow. So the speed of light is really, really fast. Way faster than the speed of sound. So think about when there's a thunderstorm happening, and did you ever see lightning strike and then you counted like 2 or 3 seconds before you heard the sound of the thunder? That's because we're able to see the light happen really quickly because the speed of light is so fast, but it takes longer for the sound of that lightning to reach us. That's why that happens. Okay, we talked about our thunderstorms. You know, I think you're ready to see how scientists draw a representation, a picture of what a sound wave looks like. You might have seen this before, especially with your classroom teacher. A sound wave is how we represent the sound and the molecules moving in the air. And it just looks like this. And we have a couple words that we use to label the different parts of a sound wave. We call this part from the top of a peak, from the peak to the next one, to the next peak. That's called the wavelength. Wavelength. And we're going to see here in a second how different sounds make different wavelengths. And we also have, if we split this sound wave in half, we have this part from the bottom to the middle of the sound wave is called the amplitude. And we'll see that the amplitude's going to change depending on how loud we make our sounds here in our experiment. All right, so Mr. Chadwick is here, and we're going to show you, using one of Ms. Bracey's jump ropes, what a sound wave looks like. So we'll get turned around. Perfect. All right. So we have our jump rope here. Now, we're going to think of let's do a low sound first. So a low sound, like if somebody was singing like this or we were playing a big tuba or a bass drum, is going to have a bigger wavelength. So Mr. Chadwick, we're going to move this on the floor up and down, but slowly, like a low sound. So we're not going to have tight curls and curves in it. It's nice and loose, a big wavelength for a low sound. But if we had a high instrument, like a flute or somebody singing soprano or opera, then we would have really small wavelengths. So we're going to have to move this sound wave up and down pretty quick for a high sound. Really tight, back and forth. Little wavelengths come from high pitches, and big wavelengths come from low pitches. Now we are in the music room after all, so I'm going to grab some instruments, and for our last little part of our lesson, we're going to test out some instruments and sounds and compare their wavelengths and their amplitudes. Now, if you want to do this at home and you have a tablet or some type of a computer that you can download apps on after you ask your parents, and it is free by the way, I can post this on Teams if you're interested. It's this little app called Audio Visualizer. If we put that on our iPad and then we talk, every sound that it hears, it shows you a picture of what the sound wave would look like. So let's test out something high pitched first. Let's make sure we can see. Okay, there we go. Let me grab something that makes a high sound, like our finger cymbals. So if I play my finger cymbals, what do you think will happen to the wavelength, the distance from one wave to the other? It should be really small. Let's see. Wow, that's so small. You can see it. Look right after I play. Tiny little spaces between the waves. Another high pitch that I can hold for a little longer so that you can see it for a little longer is from my recorder. So let's watch what the sound waves from a recorder look like. You can see the tiny little spaces between the peaks of the waves. How about our gong? The gong should be a little bit lower, so the space from one peak of a wave, the wavelength, should be bigger. Let's check. Watch again. There's a little more space between the wavelengths. Now I'm going to go as low as I can on Mr. Dundore's trombone. Okay, a trombone is in the brass family, so we know that it should make a low sound. Miss Dundore is not a brass player or a trombone player, but I'm going to do the best I can. No laughing. Okay, let's try a low sound and see how big we can get the wavelengths. Pretty good. Now I'll try some different pitches on my trombone. Did you notice that the amplitude is changing? Remember, the amplitude is where it gets taller when I play louder and shorter when I play quiet. Watch, I'll play quiet. And now I'm going to try and make it taller by playing loud. Wow, sorry if that was really loud, but we sure got a big amplitude on that one. Okay, boys and girls, we did a lot of experimenting with sound waves today. Hopefully you got a better idea of what a sound wave looks like if we were to represent it in a drawing. And you understand that these little things in the air are called molecules, and that's what's being bounced around and bumping into each other whenever a sound wave creates vibration in the air. You learned about wavelength. We learned about amplitude. What I'd like you to do is use all the stuff we did today in our experiments in our music lesson and apply that to what your teachers are doing with you in your science assignments and your science lessons in teams. For now, that's all I have. I will see you in teams on Wednesdays from 12 to 2, and send me an email if you have any questions or comments for me. Bye!